The feedback I got was that you guys said you love those circuit diagrams for RTDs. Okay, well, here's some more for thermocouples. Let's start by trying to measure the thermoelectric voltage of a type T thermocouple. Should be simple, right? We would like to read V1, the thermoelectric voltage produced by heating junction J1, the intersection of a stretch of copper and Constantan wire. We connected the copper and Constantan leads to the copper terminals of our voltmeter, and oops, we created another junction of dissimilar metals where the Constantan lead meets the copper terminal at junction J2. So what, you say? Well, here's what. You just introduced a back EMF thermoelectric voltage to V1 on the Constantan wire, and you can no longer correctly read V1. Oh no, you say. You have reintroduced doubt just when we thought all the doubts were cleared up with the RTDs. I'll take care of you. Let's add a copper lead wire at junction J2 in the picture. This way, at least, we'll have a standard copper-to-copper connections at the voltmeter. To calculate our thermoelectric voltage V1 at junction J1, we must first know the temperature at junction J2. Now, 50 years ago, people really did this by putting the leads of the dissimilar metals at junction J2 in a bucket of ice water. This forced the temperature at J2 to exactly 0 degrees C, and the term ice point reference was born. You can assume quasi-linearity of the thermocouple curve and select the local slope B. By Kirchhoff's law, yeah, that guy, the voltage V at the voltmeter is equal to V1 minus V2. Let's use the linear approximation technique we mentioned earlier and switch to 0 degrees to 273 degrees K. V equals little b times the temperature at junction 1 plus 273 degrees K minus the temperature at junction 2 plus 273 degrees C, and doing the subtraction, you would get V equal to B times the temperature at junction 1. So 50 years ago, people would read the voltage at the voltmeter, divide by little b, the local slope of the thermoelectric curve, and get an estimate for temperature. But, we're in the 21st century, and it's no longer 50 years ago. Oh, and yeah, and lugging around ice baths, that's a real drag, and they're really heavy, too. Sorry! Doubt is back again. Well, here's another circuit diagram for you. This one will work for any type of thermocouple and not just type T, which has that one copper lead. We'll illustrate it using a type K thermocouple. Let's insert an isothermal metal block into the system. Isothermal meaning constant temperature. This block creates a junction of dissimilar metals, junction J3, where the copper wire meets the chromel wire, and I abbreviate chromel with a CH. Let's substitute an isothermal metal block at junction J2 for the ice bath that we had before. In addition, we'll string some chromel wire in between these two isothermal blocks. This gives us two more junctions of dissimilar metals, junction J4, where copper wire meets chromel wire, and junction J2, where chromel wire meets alumel wire, abbreviated with the letters AL. J3 and J4 are sitting together on an isothermal block. These two copper to chromel junctions introduce equal and opposite thermoelectric voltages into the loop. And that means they cancel out. So now the voltage V is given by V1 minus V2, which is equal to little b times T1 minus T2. Of course, Now we got one equation and two unknowns, which we can't solve, but we'll deal with that in the next slide. This is the part where we combine the two isothermal blocks into one big one. Have you ever heard of the empirically derived law of intermediate metals? I didn't think so. Well, guess what? Before I studied thermocouples, I never heard of it either. But anyway, this law of intermediate metals says that when you insert a third metal between the two other dissimilar metals at an isothermal block, that your thermoelectric voltage won't change. So let's apply this to our big isothermal block. What this means is we can ignore the chromel connector wire between junctions J2 and J4. And the system will function the same as if that alumel wire on the right was connected directly to the copper wire. Note that the equation V equal to V1 minus V2 still applies, as we haven't introduced any new thermoelectric voltages. This slide shows our simplified system. Now we are going to perform a process step known as cold junction compensation, or CJC for short. We originally substituted our isothermal block of unknown temperature for the ice bath, which had a known temperature of 0 degrees C. Now we need a way to measure the block temperature without using a thermocouple. We could use either a thermistor or an RTD to do this. We prefer a thermistor because it can be packaged into a small space, and our isothermal block will always have a temperature within the thermistor range. We then take the measured block temperature and find its equivalent thermoelectric voltage for a type K thermocouple. This is voltage V2. Next up, we use our voltmeter to measure V. We then calculate V1 equals V plus V2. Now that we know V1, we use our thermocouple lookup tables to finally get T1, our goal all along. Cold junction compensation is implemented in every process instrument with thermocouple input. Here's one real-world example of how this is done. The GraphTech Model 840 data logger has a terminal block at the top. Users connect thermocouple wiring from external thermocouple probes to this block. The terminal block implements the isothermal terminal block shown in the previous slide. The temperature T2 of the block roughly corresponds to the ambient temperature where the data logger is located. But a thermistor inside that terminal block measures the exact block temperature. Let's find the thermocouple probe online. This straight probe from Automation Direct has a pipe plug on it for screwing it directly into the wall of a furnace or an oven. You can buy it as a type J or K calibration with a 1/4 inch, that's 6.3 millimeter outer metal sheath made of either 316 stainless steel or Inconel. Both of those sheath materials do stand up very well to the corrosive environment of a furnace. The magnesium oxide internal insulation in the probe protects the tiny thermocouple wires from damage during the extreme heating and cooling cycles that the probe undergoes. The ungrounded junction means that the thermocouple wires are not electrically connected to the probe sheath. American Standards Testing Materials Spec 230, that's ASTM Spec 230, governs the accuracy of thermocouple sensors, which is nominally 0.7% of reading, but at least 2.2 degrees C. This means that at temperatures lower than 293 degrees C, you will always have an error in your reading up to 2.2 degrees C. And above 293 degrees C, your error will be up to that 0.75% of whatever temperature you're actually measuring. If you need to fit the probe into a tight location, you can bend it at a right angle without damaging those internal wires, but you need to make sure that you supply at least a 1/2 inch bend radius, that's a 12 millimeter bend radius. The spec mentions a minimum installation depth of 3 inches, which is 76 millimeters. This means that you must have the probe inserted at least 3 inches, or the 76 millimeters, into the furnace or oven in order to get an accurate reading. Otherwise, the thermal mass of the probe outside of the furnace will be enough to conduct away the internal heat within the probe tip, which gives you an incorrectly low reading. You select a part number to order based on the mechanical specs you need. The probe comes in 3 standard lengths. The Type J probe can only measure up to 720 degrees C. This is a little lower than the 760 degrees C shown on the ITS 90 spec. Some manufacturers will quote a lower maximum temperature for thermocouple if they think they can't hold the full accuracy spec throughout the range. The Type K probe will work reliably up to the upper range of its calibration, in this case 1249 degrees C, but only if you specify the Inconel material for the probe sheath. The 316 stainless steel probe sheath would corrode at this temperature and ruin the thermocouple inside. Let's recap. We discussed the principle of cold junction compensation and how to specify thermocouples for use in your embedded circuit. And that wraps up this week's module on thermal sensors.